Download this code from codegive.com, link in the description below. Depth First Search, DFS, Algorithm, a comprehensive guide. Depth First Search, DFS, is a fundamental graph traversal algorithm that explores a graph or tree by going as deep as possible along each branch before backtracking. It systematically visits all vertices of a graph by following edges until a vertex is reached with no unvisited neighbors. Then, it backtracks to explore other branches from previous vertices. This tutorial will provide a detailed explanation of the DFS algorithm, its principles, implementation, applications, and performance considerations. 1. Conceptual understanding. Imagine you're navigating a maze. DFS is like picking a path at each intersection and continuing down that path until you reach a dead end. Then, you backtrack to the last intersection where you had another unexplored path and try that one. This process repeats until you've explored the entire maze. The key idea behind DFS is to explore one branch of the graph as deeply as possible before moving to another. This depth-first nature is what distinguishes it from other traversal algorithms like breadth-first search, BFS, which explores all neighbors at the current level before moving deeper. 2. Core principles. Starting point DFS begins at a chosen route or starting vertex. Exploration from the current vertex, it explores an unvisited adjacent vertex. Recursion /stack the exploration process is often implemented recursively or using a stack data structure to keep track of the path taken. The recursion naturally maintains the path for backtracking. A stack can be used to manually maintain this path when recursion isn't desired or feasible. Marking visited vertices to avoid infinite loops and revisit vertices unnecessarily. DFS marks each visited vertex as visited before exploring its neighbors. Backtracking when a vertex has no unvisited neighbors, DFS backtracks to the vertex from which it was reached to explore any remaining unvisited neighbors. Termination the algorithm terminates when all reachable vertices from the starting vertex have been visited. 3. Algorithm steps. Recursive implementation. 1. Mark the current vertex V as visited. 2. For each unvisited neighbor U of V**. Recursively call DFS on U. Algorithm steps, stack-based implementation. 1. Create an empty stack S. 2. Push the starting vertex V onto the stack S. 3. While the stack S is not empty pop a vertex V from the stack S. If V is not visited mark V as visited. For each unvisited neighbor U of V*. Push U onto the stack S. 4. Code example, Python, recursive. Explanation DFS _recursive, graph, vertex, visited, this function takes the graph, the current vertex being visited, and a visited set as input. Visited.add, vertex, marks the current vertex as visited. This is crucial to prevent cycles and infinite loops. Print, f visiting, vertex, this line simply prints the vertex being visited. You can modify this to perform other operations on the vertex if needed. For neighbor in graph vertex : iterates through the neighbors of the current vertex. If neighbor not in visited checks if the neighbor has already been visited. If not, it proceeds with the recursive call. DFS _recursive, graph, neighbor, visited, this is the recursive step. The function calls itself with the unvisited neighbor as the new starting vertex. This continues the exploration down the current branch of the graph. Code example, Python, stack-based. Explanation asterisk. Asterisk DFS underscore iterative, graph, start underscore vertex, asterisk this function takes the graph and the starting vertex as input. Asterisk visited equals set, asterisk initializes a set to keep track of visited vertices. Asterisk stack equals start underscore vertex asterisk creates a stack and pushes the starting vertex onto it. Asterisk while stack asterisk the loop continues as long as the stack is not empty. Asterisk vertex equals stack dot pop, asterisk pops the top vertex from the stack. This is the vertex that will be visited next. Asterisk if vertex not in visited asterisk checks if the vertex has already been visited. Asterisk visited dot add, vertex, asterisk marks the vertex as visited. Asterisk print, f visiting, vertex, asterisk prints the visited vertex, can be replaced with other operations. Asterisk neighbors equals list, graph vertex, and neighbors dot reverse, asterisk reverses the order of neighbors before adding them to the stack. This is important to maintain the same exploration order as the recursive implementation. Without reversing, the order in which the neighbors are visited will be different, leading to a different DFS traversal. This step ensures that the leftmost unvisited neighbor is explored first, mimicking the behavior of the recursive DFS. Asterisk stack dot append, neighbor, asterisk pushes the unvisited neighbor onto the stack. 5. Graph representation. The graph parameter in the code examples is represented as a dictionary, adjacency list. This is a common way to represent graphs in code. The keys of the dictionary are the vertices, and the values are lists of their adjacent vertices, neighbors. Example. This graph represents the following connections. Asterisk A is connected to B and C. Asterisk B is connected to D and E. Asterisk C is connected to F. Asterisk D is not connected to any other vertices. Asterisk E is connected to F. Asterisk F is not connected to any other vertices. 6. Running the code examples. To run the code, you need to define a graph and call the DFS function. Here's an example. Output may vary slightly depending on neighbor ordering in Python dictionaries before Python 3.7. Note the different traversal order between the recursive and iterative versions. This is due to the order in which neighbors are added to the stack, reversed in the iterative version to mimic the recursive call stack. The iterative version may revisit f due to the way it handles backtracking with the stack, but it correctly identifies all reachable nodes. 7. Time and space complexity. Asterisk time complexity asterisk O, V plus E, where V is the number of vertices and E is the number of edges in the graph. This is because DFS visits each vertex and explores each edge at most once. Asterisk space complexity asterisk. Asterisk recursive asterisk O, V, in the worst case, example a skewed tree or long chain, due to the call stack. Asterisk iterative asterisk O, V, in the worst case, due to the stack storing vertices to be visited. In practice, the stack size will depend on the maximum depth of the graph. 8. Applications of DFS. DFS is a versatile algorithm with numerous applications in computer science and other fields. Asterisk finding connected components asterisk DFS can identify all connected components in an indirect graph. Asterisk cycle detection asterisk DFS can detect cycles in a directed or indirect graph. Asterisk topological sorting asterisk DFS is used to perform topological sorting in a directed acyclic graph, DAG. This is useful for scheduling tasks with dependencies. Asterisk path finding asterisk DFS can find a path between two vertices in a graph. However, it doesn't guarantee the shortest path, BFS is better for that. Asterisk maze solving asterisk DFS can be used to find a path through a maze. Asterisk game playing asterisk DFS is used in game playing algorithms to explore possible game states, example in AI for chess or Go. Asterisk web crawling asterisk web crawlers use DFS, or BFS, to traverse the web and index web pages. Asterisk solving puzzles asterisk it can be used to find solutions to puzzles like Sudoku or Ken by exploring possible assignments. Asterisk bipartiteness check asterisk determining if a graph is bipartite, can be colored with two colors such that no adjacent vertices have the same color. 9. Cycle detection with DFS. DFS can be easily modified to detect cycles in a graph. In the recursive implementation, we can maintain a recursion stack in addition to the visited set. The recursion stack keeps track of the vertices currently in the recursion path. If we encounter a vertex that is already in the recursion stack, it indicates a cycle. Explanation of cycle detection asterisk. 1 recursion underscore stack equals set, a set to track nodes currently in the recursion path. 2 recursion underscore stack dot add, vertex, add the current vertex to the recursion stack. 3 elif neighbor in recursion underscore stack, if we find a neighbor that is already in the recursion stack, we've detected a cycle. 4 recursion underscore stack dot remove, vertex, remove the vertex from the recursion stack when we're done exploring its subtree. This is crucial for correctly detecting cycles in more complex graphs. 10. DFS versus BFS. DFS and breadth first search, BFS, are two fundamental graph traversal algorithms, but they differ in their approach and have different strengths. Feature DFS BFS. Exploration order depth first, explores deep before wide breadth first, explores wide before deep. Data structure recursion, call stack, or stack queue. Path finding not guaranteed shortest path guarantees shortest path. Memory usage can be more memory efficient if the graph is sparse and deep paths exist can be more memory intensive for graphs with high branching factors. Cycle detection easier to implement directly requires additional logic. Implementation often simpler to implement can be more complex. Application cycle detection, topological sorting shortest path finding, level order traversal. When to use DFS asterisk. Asterisk when you need to explore deeply into a graph or tree. Asterisk when memory usage is a concern and the graph is relatively sparse. Asterisk when you need to detect cycles in a graph. Asterisk when you need to perform topological sorting. When to use BFS asterisk. Asterisk when you need to find the shortest path between two vertices. Asterisk when you need to explore all vertices at the same level before moving to the next level. Asterisk when memory usage is not a major concern. Asterisk when you want to find all nodes at a certain distance from the starting node. 11. Optimization techniques. Asterisk adjacency list representation asterisk using an adjacency list, as shown in the examples, is generally more efficient than an adjacency matrix for sparse graphs, as it only stores the existing edges. Asterisk iterative implementation asterisk in languages with limited recursion depth, an iterative implementation using a stack might be necessary to avoid stack overflow errors. Asterisk early exit, pruning in some applications, you can optimize DFS by adding conditions to stop exploring a branch early if it's clear that the desired solution won't be found in that branch. This is known as pruning. 12. Conclusion. DFS is a powerful and versatile graph traversal algorithm with numerous applications. By understanding its principles, implementation details, and trade-offs compared to other algorithms like BFS, you can effectively apply it to solve a wide range of problems involving graphs and trees. The choice between the recursive and iterative implementations often depends on factors like language limitations, memory constraints, and code readability preferences. Always remember the crucial role of marking visited vertices to avoid infinite loops and ensure the algorithm terminates correctly. Remember to reverse the neighbors list in the iterative approach to mimic the call stack of the recursive approach.